Hello everyone. So today we have the following problem. Set up the integral describing the area of the large loop, but outside the small loop of the limacon r equals 1 plus 2 sine theta. Sometimes we say find the area outside the inner, inside the larger, something along those lines. And we're looking for the area in green that you see. And if you take a look at what we're given here, we erase it. Stuff in green, yeah, this is the limacon, and go back, yeah, we're going looking at that stuff in green. Okay, so two things before we even get into setting up an integral here. For me, yeah, the integral itself is actually easy to compute. The setup is the hard part. I think what happens a lot of the time is a lot of students, they know what the graph looks like or they memorize it, which is very important just to know what it is. But the biggest issue that I see when I see mistakes made with these types of problems are that a lot of students don't take the time to draw out the graph or see how it is drawn out. Okay, and getting into that right now, let me draw out the graph of r equals 1 plus 2 sine theta, where you have an r theta axis, the theta just being like the x, the r like your y. So I'm just going back to what you would have graphed with a, what you were learned in your pre-calc or your trigonometry classes when you're graphing trigonometric graphs. That's all this is, okay? But just written in that form. And that's gonna help us to see how this is like traced out. In green, those are places where your r equals 0 and 7 pi over 6 and 11 pi over 6. And furthermore, those are like the places where your loop, your inner loop, small loop, I'm sorry, is formed, okay, where r is 0. Okay, now let me go back to the graph just to show you how this would be traced out. So in our case, if you look at the graph, the amber one, the one like an orange, at theta equals 0, you start with 1, which would be here. And if you trace this out accordingly, as theta gets bigger, r will get large up to when you get to pi over 2, which is right here on that graph. And starting at pi over 2, graph traces this out until you reach 7 pi over 6 and your r would be 0. Okay, so between, and let me make a note of that, between pi over 2 is right here, and then 7 pi over 6 is right there. And I would say this: if you set up an integral that goes from 7 pi over 6 to from pi over 2 to 7 pi over 6, that would describe this region right here. It's actually half of the whole limacon. And if you multiply that by 2, you would actually get the whole area of it right here. So let me set up an integral saying that. And so twice of the integral of 1/2 of pi over 2 to 7 pi over 6 of 1 plus 2 sine theta squared d theta. That would describe that, yeah, the whole limacon. And now I'm going to subtract the area for the inner loop. And how do I get that? Well, let's go back to our tracing here. Yeah, so at 7 pi over 6, we were right here. Let me zoom in. And then if you looked at back up here where I drew that the graph out on r theta axis, your r is negative from 7 pi over 6 to 11 pi over 6. So normally where you would be graphing somewhere here, all of that gets graphed over here, okay, because your r is negative. And if you recall, when r is less than 0, it's moved over 180 degrees, either clockwise or counterclockwise, whichever direction you prefer. Okay. And likewise, from 3 pi over 2 to 11 pi over 6, your r is negative, so everything that would be normally drawn in the fourth quadrant of r was positive is now drawn in the second quadrant because you turn it 180 degrees. And that inner loop is between those two angles, between 7 pi over 6 and 11 pi over 6. So if you subtract 1/2 7 pi over 6 to 11 pi over 6 of 1 plus 2 sine theta squared d theta, that would describe that inner loop. And yeah, I can think of it as like the red stuff minus the blue. Then that would be the area that we're looking for. One thing I wanted to mention here is a mistake that often people make with these problems is they'll say, oh, you know, I'm going to take so let me just write wrong here because this won't be correct. This is like saying the area for that outer loop is equal to going from 0 to 2 pi, 1 plus 2 sine theta squared d theta minus 1/2 that inner loop, 11 pi over 6 to 7 pi over, 11 pi over 6 to the top limit and 7 pi over 6. They'll often say something along those lines. Now, the reason that is incorrect is because you're adding more area. We're quote unquote double counting. Because if you go back to your graph here, and if you were to look at how much area you'd be looking at with those limits of integration, well, if you went from starting at 0 to pi over 2, you're looking at all this area right here. From pi over 2 to pi, you're looking at all this. Oops, let me erase that little chunk there. So notice how you're already including the inner loop. And then from pi to 7 pi over 6, you got this little chunk. And then you're going to include the loop again from 7 pi over 6 to 11 pi over 6. And then finally, from 11 pi over 6 to pi over 2, you got that. So you basically counted that inner loop twice in your area. Okay. So when you write this out, you counted it twice here for that integral from 0 to 2 pi, and you subtracted, when you do the subtraction, yeah, you subtract the area of the inner loop, but you still have one inner loop in there that you're including, so, excuse me. So that's why this is incorrect, and it's wrong. And I've seen this mistake often with a lot of other problems, and if I were to say why this is the case, it's a lot of the time because people don't realize how the graph is traced out, and because of that you're adding more things here. Okay, so just be aware of that when you're graphing and you're trying to set up an integral, that you're often you could count things twice if you're not careful. Okay, all right, well, thank you for your time, appreciate it.